All right, welcome back. If you've been following along, this has been a little bit of a long dive into AP Physics 2, electric field force and potential. And we've gone through the equations, and we've actually taken a look a little bit at some of the units that represent our electric field strength. But we've been doing all this so that we could really dive into this AP problem. So let's finally get started on this. And we're probably going to dive kind of deeply into the concepts on this one as well. So hopefully you stick with me and watch this video and learn a little something about electric potential. So they give us something called isolines of electric potential. All right. Now, some of us may not have seen isolines of electric potential, but you should understand what an isoline is. So an isoline is a line where every point on that line has the same value. So I'm just going to take a really simple positive charge. Let's just take this is irrelevant to this problem. We know what the electric field lines look like around this, right? So they all point outwards. And you've seen this before, maybe. The more lines coming out, the stronger your charges. And also, something else, these are electric field lines. The closer together those field lines, the stronger your electric field at that location. So those two things should be, things that you got a good grasp on. So first, when I look at this, you might see that the spacing, if I drew a circle around here, and my picture is not perfect, but this space and this space and this space and this space, all these spaces are about equally spaced, right? So that might give you the idea that, okay, these all have the same electric potential, but maybe that's not enough for you. Maybe just looking at it, that's not a very good proof. That's not very rigorous. Let's think about, this said, isolines of electric potential. So we know our electric potential, V, is represented by this equation. V equals KQ over R. So let's write that down. KQ over R. This is V. So that means that Q is not changing because Q is based on my charge itself, right? So this charge is not changing. K is a constant, so that can't be changing. So the only way to get a different V is to change my distance. So at all of these points, distance, distance, all of these points in a circle around my charge, all of these are at the same distance. So at this location, R is the same for every point on the circle, which means this red ring has some equipotential. So all points on that red ring have the same electric potential. And if we go out a little bit farther, all of the points on this circle are the same distance, right? If I drew from the center of our charge out to here, that's the radius. And so that radius is the same for the circle all the way around. So this has some different V, right? And if it's getting bigger, this bottom number is getting bigger, so our V is actually getting smaller. So we have, no matter what, we could walk our way out from that point and get all different V's. They would get smaller and smaller as we get away from our charge. So hopefully the idea of an isoline should kind of start to make sense. But now when we have two charges here, we have to say, okay, well, what does that mean? Well, let's just take two charges. I'm going to make them, in this case, just for us to start wrapping our heads around this, let's just say that they have the same charge. And I'm going to make two cases. One case where they are either both positive or both negative, I don't care. And then the other case where one is positive and one is negative. Okay, so same signs, opposite signs. So in that case, same signs. We know positives have electric field lines that stick out, and they're going to kind of bend away from each other. Pardon my kind of sloppy drawing. And these bending lines okay? And in this case, so these are electric field lines, just as they were before up here, right? All my arrows that I'm drawing are electric field lines. And in this case, they go out of positives and into negatives. So we get a different shape. Okay? Always out of the positive and into the negative, right? So, well, that should be very familiar. We should know about the electric field lines. What does that mean for isolines? Okay? Let's think about this equation and in terms of these two charges. If I was to have let's draw this one. Some location, let's say some distance away. At that location, we would have some v based on q from this, k is a constant, and the distance. And if I move that same distance over here and over here, right, all the way around here, they would have, just caused by this one, we're not even talking about this one, all of these points on this circle would all have the same v, just as we said before when we had a single charge. Now, what if, not what if, this is what's going on. We took a similar point somewhere in space, and then we said, okay, this has some v. And then we drew a circle around that. There will be points where these v's overlap. And if these are both positive, so positive, positive, at this location, we're actually going to get these two positives adding up, right? They're going to increase the v at this location. There will be an even stronger v here because those two fields add together. I said fields. Electric potentials, not fields. Now, let's think about that here. If I have some location, there will be some v from this positive, right? And we know that all the way around this, so remember, we've kind of divided this. These are not, they're not two totally isolated systems. So everywhere on this blue circle, we end up with some positive v. But a negative charge will create, well, the negative goes in for q, will create some, at some location, a negative v. And for simplicity's sake, if we said these q's in all cases have equal magnitude, so these two, that means the purple v at that location would be doubled. And in this case, what's going to happen? At this location, the positive and the negative v, these v's will cancel. Okay? So, and you could imagine this, right, for infinite rings around our two charges. So everywhere where those two rings cross, there's going to be, so there's a little bit smaller of a ring. Those two rings would intersect here. You go a little bit bigger with both rings, and they're going to intersect a little bit farther away. And hopefully over time you see that you're going to get this dividing line down the center all the way from here off until infinity, where v equals 0. Now in this case, you never have a v equal to 0 between your two charges. This has positive potential. It's positive potential, positive potential. Everywhere in between here, there's some positive potential, right? Over here, it's mostly due to this, with a little bit of the pink one added on. Close to the pink one, it's mostly due to the pink one, with a little bit of blue added on. But we have positive potential everywhere in between these two shapes. Here we have, on the left-hand side, positive potentials. I'm going to actually, these are positive over on this section. We're going to have some dividing line where our potential is 0. And here on the right-hand side, because this pink charge now in this diagram is negative, we have negative potentials over here on the right. Okay. So the short version, hopefully that really makes sense. The short version, the shortcut, now that you've seen it and we've kind of worked our way through what these are going to look like, is that when we have isolines for electric potential, if you have two charges and you have some rings around here and some rings around here, and at some point those rings kind of merge into one ring that envelops both shapes. In this situation, these charges are the same. They could be both positive, they could be both negative. That's the short version of this, okay? All that beginning stuff, if hopefully you watched it, but if you skip straight to this point, now you should be able to recognize, if you just see isolines of electric potential, these have similar charge. Now on the right-hand side, if we go to this picture, and we have two charges, you will see the similar rings around those charges, but at some point, you're going to see a line that divides them, okay? And that line is going to be your 0 electric potential, okay? This means you could have a positive and a negative, or a negative and a positive, but they have opposite signs. Now, the problem that we're looking at here, one of those charges is a little bit stronger than the other. So in one of these cases, that means that these rings, I'm going to actually draw right over it, push away from this charge. So you actually end up with more rings around this one. And this one may only have a few. And then you're going to have a bigger ring and a smaller ring that envelop both. Okay? So if you look at the picture on the AP question that we're looking at, around Y, there actually are more rings getting closer and closer to Y that they didn't draw. Okay? So I believe if you read the problem, the outermost that's around everything has a potential of 50 volts. And as we walk our way closer to Y and closer to X, they go up by 10. So 50, and then line A is 60, and then 70, and line B is 80, and between is 90, and C, all the way close to Y, is actually 100 volts. But you're going to, as you go closer and closer to Y, those right here, you're going to get, 110 and maybe 120. We don't know exactly, but there'd be more rings in there. Just know that there would be more rings in there, okay? And then over here, you would have less rings working their way towards X. Okay, so that would be how it would look if they were out of balance in that case. All right, so here, what happens is our purple line that divides the positive and the negative half, or vice versa, gets shifted, right? Because we're looking for a place where V is equal for both. So if Q is really big on one side, I'll do again on the right, the Q is larger here. That means that if this is really big, for V to be the same, this has to be bigger also, right? So here, closer to our weak charge is where our 0 point would be. And it's actually not going to be a straight line, right? So this is going to have some curve to it. And actually, my question for you is something that I want you to think through. Is that curve going to curve towards the greater charge? Or is that curve going to be pushed away from the greater charge? It will have a curve to it. Which of those two curves do you think it might have? And you should be able to, think your way through this equation and figure out which of those two curves it is. And I hope that gave you a little insight into this problem. We're not going to go through every part of it, but at least I wanted you to understand what that diagram of isolines of electric potential are. Hope that helped. Take care. Good luck on the test.